real zeros of polynomial functions. Let's begin by reviewing how to evaluate a polynomial. To evaluate a polynomial at an argument, first substitute it in for any x value and then simplify. So we have to find p of -1, p of 0, and p of 1. So first for -1, wherever an x appears, we substitute -1 in place of x, and then we evaluate and simplify. -1 to the third is -1. -1 squared is positive. 1 times 5 is 5. -6 times -1 gives us positive 6, and we have a plus 5. And then if we add all of these terms up, we end up getting 15. If we substitute 0 in to each x location in the polynomial, we'll have 0 cubed plus 5 times 0 squared minus 6 times 0 plus 5. So it's zeros for the first three terms plus the 5 at the end, so it just simplifies to 5. And if we substitute 1 in, evaluate and simplify, we end up with 5. Now let's look at another approach. A process called synthetic substitution is an alternate way to evaluate a standard form polynomial function at a given argument. If we have our p of x function and we are asked to evaluate it at -1, we can create the synthetic substitution array as shown below. We take all of the original coefficients and constants of the polynomial and we write them without any variables next to them, all in a row. We also take the x value that we are using to evaluate the function and we place it in a box. We bring the first one down, or the first coefficient down, and then we multiply -1 times that coefficient that we brought down, and that's going to be -1, and then we're going to add vertically. You multiply on the diagonal by -1, or the x value that you're using, and then you add vertically. And we continue to use that process as we work through the array from left to right. So when we add vertically here, we end up getting 5 minus 1, which is 4. Then we're going to take that 4, multiply it by -1, and we get -4, and then we're going to add vertically. -6 plus -4 is -10. The final step is multiplying the -10 value that we found by -1, which is positive 10, and then adding vertically, and we get 15. A completed synthetic substitution is shown below. Synthetic substitution allows us to evaluate a polynomial function value through an iterative algorithm of multiplying followed by addition in a careful way. Now, why does this work? An unusual way of grouping and factoring the polynomial will help us understand why synthetic substitution works. Carefully review the grouping and factoring pattern and you'll understand. So we first take our p of x function and we group the first three terms together because they all have a variable x in them, and factor them out. Factor an x out. Then we're left with x squared plus 5x minus 6. Then we're going to group the x squared and 5x together and factor out another x. So we have x plus 5 times x, and then we have that whole thing subtracted by 6, grouped together, multiplied by another x, and then plus 5 at the end. So now if we take -1 and substitute it in for all the x values, -1 plus 5 gives us 4 times -1 is -4. -4 minus 6 is -10 times -1 is positive 10 plus 5. Notice that each of these expressions boxed in green, red, and blue correspond to the columns for synthetic division, meaning that it mirrors the process of adding and multiplying repeatedly. Recall that a 0 of a polynomial is an input that gives an output value of 0. The number z is a 0 of polynomial p if and only if p of z is equal to 0. A 0 is also called a root. These two words are interchangeable. With polynomial functions, real zeros correspond to real numbers on the x-axis, where the graph of the polynomial touches or passes through the axis. Is 2 a 0 of p of x, which is equal to x cubed minus 5x squared plus 3x plus 6? There are a couple of different ways to see whether or not 2 is a 0 of our polynomial. The first thing we can do is we can substitute or evaluate our p function at 2 and see if it does equal 0. If it does, then 2 will be a 0 or a root of our function p of x. So if we substitute 2 in for all the values of x and evaluate, we'll get 2 cubed, which is 8, minus 5 times 2 squared. Well, 2 squared is 4, times 5 is 20, so 8 minus 20 plus 6 plus 6. 8 minus 20 is negative 12, plus 6 is negative 6, and then plus another 6 does indeed give us 0. The other way that we can determine if 2 is a 0 of the polynomial is through synthetic substitution. We can take the leading coefficient 1, bring it down, multiply it by 2, we get 2. Negative 5 plus 2 is negative 3. 2 times negative 3 is negative 6. 3 minus 6 gives us negative 3. And then 2 times negative 3 again gives us negative 6. And we do have 0 when we add straight down. So therefore, 2 is definitely a 0 of our function p. Is 2 plus the square root of 3 a 0 of capital F of x, which is equal to x cubed minus 4x squared plus x? The first method that we're going to use is substitution, but this is a binomial that has a radical in it. So if we actually cube that, it'll be a bit ugly. So let's actually factor an x out of all of these terms first. So we'll have x times x squared minus 4x plus 1. And now if we substitute the 2 plus square root of 3 in for x, we can simplify that and see if it does indeed equal 0. So that means we're going to put 2 plus the square root of 3 out in front, and then inside we'll have 2 plus square root of 3 squared minus 4 times 2 plus square root of 3 plus 1. And then when we square this, it means that you're taking 2 plus the square root of 3 and you're multiplying it by itself. So you have to distribute. And that's how we get 4 plus 2 root 3 plus 2 root 3. So that's 4 root 3 together plus 3. And then we have this minus 4 that we have to distribute into here. So we get minus 8 minus 4 square root of 3, and then plus 1. It simplifies to be 8 plus 4 root 3 minus 8 minus 4 root 3. Oh, wait a second. These cancel out. And these two also cancel out, so we have 2 plus the square root of 3 times 0, which equals 0. Therefore, 2 plus the square root of 3 is a 0 of our function f. We can also find the solution through synthetic substitution. So again, we write down all of our leading coefficients, 1, negative 4, and 1, and then 0 because there's no constant term at the end, so we have to put a 0 in its place. Bring down the first one. 1 times 2 plus square root of 3 is 2 plus square root of 3. Add straight down, but only combine like terms. So negative 4 plus 2 gives us negative 2, and there's no square root of 3, so 0 plus square root of 3 is square root of 3. And then if we multiply these two together, it ends up being negative 1, and here's how. You're going to have 2 plus root 3 times negative 2 plus root 3. You get negative 4 plus 2 root 3 minus 2 root 3. These terms cancel out, and then you have a plus 3 at the end. Negative 4 plus 3 gives us negative 1. And then 1 plus negative 1 is 0. 0 times 2 plus root 3 is 0. And add straight down, we get 0. So this does prove that 2 plus the square root of 3 is a 0 of f. Consider the polynomial f of x and a real number s. If f of s is equal to 0, the following statements are all true. First one, s is a 0 or a root of the function f of x. x equals s is a solution of the equation f of x is equal to 0. And s comma 0, this ordered pair, is an x-intercept of the graph of the function f of x. It's worth noting that a 0 or root is a number that corresponds to the x-coordinate of an x-intercept. A 0 is not a point in the plane. Now let's review the remainder theorem. Recall that p of x, if it's assigned to be a polynomial of degree n, where n is greater than 1, then if p of x is divided by the factor x minus a, the remainder r of the division is equal to p of a. In previous examples, we had 2 for the value of a, or 2 plus the square root of 3, and in both of those cases, the remainder r ended up being 0, and it was the same whether we used division or whether we evaluated the function at the a value. So if we are given that p of x is a polynomial, q of x is the quotient of the division of p of x by x minus a, and r is the remainder of division, we have to prove that p of a is equal to r. We have that p of x over a is equal to q of x plus r over x minus a. If we multiply both sides of this equation by x minus a, we end up getting p of x by itself. Q of x is now being multiplied by x minus a, and then r is now by itself. And then if we let x equal a, we have p of a is equal to q of a times a minus a. Well, that's going to be 0, so the first term on the right-hand side of our equation will end up going away, and we'll be left with r. So therefore, p of a is equal to r. Here's an example for comparison. Here's an earlier example. P of x is equal to x cubed plus 5x squared minus 6x plus 5, and it's being divided by the binomial x plus 1. Over here to the right, we show long division. That is slow and tedious, but it does get the job done, and we find out that the remainder is 15. The remainder theorem, shown down here, is a quicker, more efficient way to find the remainder of division. Just substitute the x value from the factor, and remember x plus 1 can be set equal to 0, and then if we solve for x by subtracting 1 from both sides, we'll get that x is equal to -1. So then if we substitute -1 into p of x, we get that the remainder is 15, and we can see that using the remainder theorem is a lot more efficient than using long division. We can also use synthetic substitution to determine the remainder when we have p of x and it's divided by x plus 1, and we have done this and found that the remainder is 15. It's worth noting that synthetic substitution is useful for finding the remainder of a division problem. Let's also review the factor theorem. Let p of x be a polynomial of degree n where n is greater than 1. If p of x is divided by x minus a, this factor, and the remainder r of the division is equal to 0, then the factor x minus a is a clear factor of the polynomial p of x. So if we're given that p of x is a polynomial and q of x is the quotient of the division from p of x divided by x minus a, and r is the remainder of division, and we prove that p of a is equal to r, which is equal to 0, then x minus a is a factor. So here we have p of x over x minus a is equal to q of x plus the remainder of the division, and the remainder always goes over the divisor, x minus a in this case. If we multiply both sides by x minus a, we get that p of x is equal to q of x times x minus a plus the remainder. Now if we let the remainder be 0 based on this theorem, we would be left with p of a being equal to q of x times x minus a, making the factor x minus a factor of our polynomial p of x. Now let's extend an idea. The process called synthetic substitution is used to evaluate a standard form polynomial function p of x at an argument x equals a. The iterative algorithm of multiplying followed by adding in an array allows you to evaluate our function p at the value a. But it turns out that the same process provides even more information. The coefficients of the quotient function q of x are revealed in the iterative algorithm. Consider the division given by p of x divided by the quantity x minus a is equal to q of x plus capital R divided by the quantity x minus a. Because the quotient q of x is revealed in the process, synthetic division is a more descriptive name for the algorithm. So what's the difference between synthetic substitution and synthetic division? It turns out not much. Let's see through this example. Find the quotient q of x and the remainder r when the polynomial p of x, which is equal to x cubed plus 5x squared minus 6x plus 5, is divided by x plus 1. Well, we know that a is -1 because our factors are x minus a number, and minusing a negative changes the subtraction sign to an addition sign. So therefore a is -1. So we have p of x divided by x plus 1 is equal to x cubed plus 5x squared minus 6x plus 5, all divided by x plus 1. And if you were to do the long division, you would get x squared plus 4x minus 10 plus 15 divided by x plus 1. You can also do it synthetically. We have -1 in the box, and then we have our coefficients 1, 5, -6, and 5. Drop the 1 down, multiply, we get -1. 5 minus 1 is 4, times -1 is -4, -6 minus 4 is -10, -1 times -10 is +10, add straight down, we get 15. So we do see that these coefficient values reveal the resulting quotient and remainder. Now let's talk about repeated synthetic division. The synthetic division array can be repeated by continuing the process a second or more times vertically. Let's see this in action. If we have this new polynomial function p of x, which is equal to x to the 4th minus x cubed minus 15x squared minus 23x minus 10, and we're dividing it by the factor x plus 1, its quotient by x plus 1 again, and its quotient by x plus 2, we will end up with the following. First, when we do the division by x plus 1, our number that we put in the box is -1. Write down all the original coefficients, 1, -1, -15, -23, and -10, and perform the synthetic division. Bring the 1 down, multiply, add. Multiply, add straight down. Multiply, add straight down. Multiply, and add straight down. We see that the remainder is 0. Therefore, by the factor theorem, it follows that our original function p of x can be rewritten as x plus 1 times x cubed minus 2x squared minus 13x minus 10. So if we take our quotient that we found on the last slide and we rewrite it down here, we have 1 minus 2 minus 13 minus 10, and then we perform the synthetic division by -1 again. That's taking care of this step. This one was taken care of on the last slide, and we're doing this one now. So we drop this 1 down, we get -1, add straight down -3. -3 times -1 is 3, add straight down, we get -10. -10 times -1 is 10, add straight down, we get 0. So by the factor theorem again, it follows that our original p of x polynomial function is equal to x plus 1 quantity squared, because we had -1 synthetically divided 2 times, and we are left with x squared minus 3x minus 10. We're taking these coefficients and constants and turning it into its corresponding polynomial expression. So on the last slide, we got up to this step. So we had x squared minus 3x minus 10, and now we're going to divide that by x plus 2. So the number inside the box is going to be negative 2. Drop the 1 down. Negative 2 times 1 is negative 2. Add straight down, we get negative 5. Negative 2 times negative 5 is positive 10. Add straight down, we get 0. So therefore, by the factor theorem again, it follows that our original p of x function can be rewritten or simplified as the quantity x plus 1 squared times the quantity x plus 2 times the quantity x minus 5, which we get from our last quotient. The final theorem to discuss in this topic is the rational zeros theorem. It states that if p of x is a polynomial with integer coefficients, and if p divided by q is a 0 of p of x, in other words, the polynomial function evaluated at p divided by q is equal to 0, then p is a factor of the constant term and q is a factor of the leading coefficient. So if we let capital P of x be equal to some coefficient an times x raised to the nth power times another coefficient for the next term a with n minus 1 in subscript times x to the n minus 1, or one less exponent than our previous term, all the way down to a1 times x to the first plus a0 or a naught, then if p of lowercase p divided by q is equal to 0, then p is a factor of a naught and q is a factor of a sub n.